Alright, time for another draftphysics.com, debatephysics.com also, video presentation. So in this series of videos intended to provoke some sort of video response or something from a physicist, somebody who really knows what they're talking about actually, and can produce some sort of good reasoning or physical evidence of something countering what I'm going to describe in this video. So some sort of reasonable explanation for why anything I'm saying is incorrect and such. And I'm willing to pay somebody for the privilege of being debunked. So if you're not willing to do it for the principle, let me know how much you would require as compensation, and I'll certainly consider almost any offer. So anyway, so springs, once again. And so as I have stated earlier in a previous video, there is a truth to the fact that when springs are pushing light masses versus heavy masses, they lose efficiency. So the faster the spring is moving, when the object disconnects from the spring, the more energy that's going to be left in the spring and the more it's going to oscillate back and forth. And that can be understood as energy you didn't transfer. So obviously at higher velocities the spring will oscillate more than at low velocities when the object actually leaves the spring. So you'll trap more of the energy in springs when you're releasing or pushing something lighter than when you're pushing something heavier. When you're pushing something at a higher velocity, you'll lose more of the spring's efficiency in giving the energy back. So springs are very good at collecting energy, not so good at releasing energy. Alright, so that's the previous statement about springs, and now I'll add on a little bit. Alright, so an assertion I would make that isn't really discussed at all, as far as I can tell by physics, is when an object has force and it's going to encounter a spring connected to another object, the real argument is that what is actually the spring is going to do, and the spring is going to behave just like a piece of foam or a dent fender or some way of displacing or creating, even you could argue it's the same thing as heat, except you're storing it. So it's like losing energy to heat, except it's still in the spring and you can get it back again. But it is absorbing energy. So the force here will not get here. Okay, so while as the spring is compressing, the actual force going into this object is less than the force that the object possesses, and it's slowly losing some of its force to the compression of the spring. So there's actually less force going into this object until you reach the maximum pressure, where the pressure back created by the object you're connected to equals the pressure being applied. And in the case of gravity, because it's a constant force, it will establish an equilibrium at that pressure. And so then all the force just goes straight into whatever the supporting object is, whatever's supporting the spring. Now if this object actually moves as the spring compresses, there's a point where you break its static friction or some other argument about creating its motion. There takes a certain amount of pressure to do that. The spring will compress that much, but if the object moves, then the spring won't compress as much as it would if the object doesn't move. So obviously you're not going to get as much back if this actually does move. And so you're really storing just a component of the force. So you could argue that if the force is a per second force, gravity for example, the first portion, that force goes into the spring and it won't be felt fully by the object. So if I had a mattress in front of me and you threw a lead ball, I might only feel a little tiny bit of pressure. I wouldn't feel the whole pressure of the lead ball because the mattress is going to dissipate and absorb a bunch of it. So the same thing is true if I just had a spring. attached to me and the ball hits, I'm not going to feel the full force until the spring compresses to the maximum pressure the ball can create. And if it's not a constant force, then it's always going to be something less than half of the original force. So if you could sort of understand, I guess I can move that. So if you threw something at a spring, it's going to collect some portion of the energy, and then it's going to give it back in both directions. And what you're actually going to feel is the push back after the compression. You're going to feel the thing leaving. You're not going to actually feel it compressing, because it compressing absorbed the force. So it's really just an argument that when a spring compresses, it's absorbing force, it's using it, and therefore it can't do both things. It can't hit you and compress the spring. So while the spring is compressing, you're not going to be feeling the force, the full impact of the force. And it's not until the spring releases that you're going to feel your half of the releasing pressure. Like I said, it gets a little more complicated when you're talking about a constant force, because then you're really just arguing that the first initial part of the impact you're not going to feel. But the next second, or the next half second, or the next tenth of a second, or the next millionth of a second, you will feel the force then. But the initial amount of force, you're just getting a little bit less than the full force. So the full force that's going to be possible to feel here isn't going to be the full force that hits this surface, because the spring absorbed a portion of the force. So that's a simple argument, that springs absorb energy out of the object, and so you can't do both things. You can't compress the string, store the energy in there like heat, and apply the force to the object. Can't do both. All right, I think that's a simple enough statement. So we'll leave it there, I think. I'll pause, see if there's anything to add. All right, just go over it one more time. All right, so you have a total force that this possesses, an MV. Some portion of that MV will go into the compression of the spring. Okay, so it'll be here. And then some lesser portion of the total MV will actually get into this surface and be felt by the surface. And the simple truth is, if the surface doesn't move, you're going to get everything back, because all of the energy will be absorbed by the spring. But if the surface moves, whatever percentage of the MV is in actual movement, not idealization movement or some kind of fake movement, the fact is you collect all the energy and it'll give back all your MV will be returned. And however much energy goes into the actual surface, you know that much you're not going to get back. So again, with the case of a constant force, the illustration is more obvious in the sense that the total amount of force that you have on the weight of this object impacting the spring is going to, this surface can't possibly have to resist all of it, because there's a portion of it that's going to be in the spring. It can't be both in the compression of the spring and be felt by the surface. So the spring absorbs a set quantity. Okay, its compression is a set quantity of MV, an impulse amount of total MV, a net amount of NV that is trapped in the spring. And then the constant force can just apply the energy straight through once that initial amount of energy has been trapped in the spring. But you can't, the simple principle is you can't trap it in the spring and apply it to the object. You can't do both. And you can only do both once the spring expands. Then it can give half the energy this way and half the energy that way. But it absorbs it just in one direction. Clearly. All right. I think that's enough. So, till the next time and such. So forth and whatnot.